Hey, geometry students, it's time for another lesson in geometry, and this time we're going to be talking about tangents and circles. Notice that this is a part one lesson on tangents and circles. Now, if you recall, a tangent is a line that just barely kisses the outside edge of a circle at one point. Okay, we learned about tangents at the same time we learned about chords, which pass through 2 points on the outside of a circle, and diameters. Diameters are chords that also pass through the center of the circle, so they are actually over the widest part of the circle. All right, but tangent lines have some unique properties, and that's kind of what we're going to be focusing on in this lesson and in the part two lesson later. So let's take a look at some theorems related to those tangent lines that just barely touch 1 point on the outside of the circle. First of all, if a line is tangent to the circle, the line is perpendicular to the radius drawn at the point of tangency. The point of tangency being the point where the tangent touches the circle. So if I drew line EF here, and it was tangent to the circle at point G, then the radius DG would be perpendicular to EF. That's our first theorem. Let's take a look at our second theorem and see if it's related to that one. If a line in the plane of the circle is perpendicular to a radius, so if a line is perpendicular to a radius drawn to uh, the edge of the circle, its endpoint is on the circle, then the line is tangent to the circle. Wait a second, do those relate to each other? They have the exact same diagram with different letters. Let's see. This is the converse of this. If a line is tangent to the circle, the radius is perpendicular. If the radius is perpendicular, the line must be tangent to the circle. If a statement and its converse is true, that means that we can rewrite those two statements as a biconditional. So this is the biconditional that's true about tangent lines. A line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. If the line is not perpendicular to the radius, it is not tangent to the circle. Okay? And then theorem 58.3, if two tangent segments are drawn to a circle from the same exterior point, then they are congruent. So QM is congruent to QN in this image here. Hey, one other really interesting thing, I can draw a point on any place outside the circle, as long as I'm drawing it somewhere outside the circle. And here's the thing, there's always going to be 2 points on the circle that are I can draw tangents to from that point. So I didn't have to put Q here. I could have put Q like over here somewhere, and I would have been able to find 2 points. It would have been different from M and N, but I could find 2 points to which Q is tangent to the circle. If I move Q closer, those points are going to get closer together. If I move Q further away, they're going to get further apart. But I can always draw two tangent lines to the circle regardless of where I put Q. And then those two tangent lines, according to this, the two tangent segments from the point to the point of tangency are going to be congruent to each other. All right, let's see how these play out in practice problems. You notice I have a bunch of miscellaneous pieces of like diagrams over here. That's because the most important thing to do with these problems, as with many geometry problems, is to start by drawing them out. All right, let's get started though with letter A. Line A is tangent to circle R at point D. Point D is a point of tangency. Okay. And line B, another line passes through the point R at the center of the circle. Lines A and B intersect at point E. Okay, so we have another point that's being introduced, E. If the measure of RED is 42, determine the measure of DRE. Oh. So with this problem, you have to draw it out. There's way too much to keep track of without drawing it out. So let's draw it out. Okay, so we've got a line tangent to a circle. I'm just going to make those tangent, and then I'm going to take one of these points, and we're going to make this the point of tangency. This is going to be the point at the center of the circle. We need a radius, right? Because we're probably going to have to put that on there. And then let's see. This is line A. This is circle R. So my middle point is R. This is point D. I should probably label these points just so we keep track of them. R and D up here. Okay. That's good enough. And then let's see. This is line A. We'll label line A2. I don't want to spend all my time here labeling everything, but it's really important. All right, so there we go. And then let's see. Lines and then we have a line B that passes through point R. Notice it's not circle R, it's point R. So that means that this line is going to have to pass through R like that. This is going to be line B. Let me just extend line B a little bit. There we go. Okay. We're going to label line B. All right. I think I've got my drawing drawn now at this point. Let's see. I'm going to make sure that this is far enough away from line A that it doesn't get confused with it. There we go. That's pretty good. Okay. Now, one more. They intersect at point E, right? So we're going to take point E and put it on the intersection the best we can. That's probably about right. There we go. Okay, so the question is this. Now, without drawing this out, by the way, you might not have realized that line E has to be locked into a pretty specific place. Point E has to be locked into a pretty specific place because it's on the tangent line. And it's on at the intersection of the tangent line and a line that passes through the center of the circle. So if I know that RED is 42 degrees, so I'm just going to label that. Let's see, so this inside here is 42 degrees. Okay. Can I figure out what DRE is? Well, here's the other thing we know. We know that this up here has to be a right angle. It has to be a right angle because it's a tangent line. And according to our first theorem, remember, it says if a line is tangent to a circle, the line is perpendicular to a radius. So this has to be a right angle. We know this is a right angle. This is 42 degrees. That's a total of 132 degrees it's already taken up. We need to figure out what this angle has to be. It's going to be 48 degrees. So by drawing it out, I was able to figure out that angle DRE has to be 48 degrees. All right, and then poof, you'll see that I changed the drawing now to match letter B instead. It takes a long time to set these up, so I just set it up while I was off screen here. So let CA be the radius of circle C. Let M now be the tangent line to C at point A. And then we're going to put a point B somewhere as an exterior point, okay? I put point B here initially, but we can move this because it doesn't have to be right there. So let's see, point B could be like over here, could be up here. What does it say about point B? The measure of BAC has to be less than 90 degrees. So that means that the measure of BAC B has to be somewhere down here to be less than 90 degrees. Is AB tangent to circle C? Um, there's no way for me to draw a line through A and B. Let's just see what I can do here. Can I draw a line from A and B that doesn't pass through another point of the circle? If I was better at aiming, maybe that would help. Let's see if we can fix this. So the question is, can I draw a line that goes through A and B that only passes through one point of the circle? I can get kind of close, but I don't think I'm going to be able to do it because of that pesky second theorem that we have here. And if I zoom in, you'll notice that I'm passing through at least 2 points. I'm passing through exactly 2 points of the circle. AB is a chord. It's not a tangent. And the reason for that is because if a line in the plane of the circle is perpendicular to a radius at its endpoint on the circle, the line is tangent. This is never going to be perpendicular to the radius if this angle is less than 90 degrees. So that's my problem. No, the answer is no, and it's because of that theorem. Um, if according to 58.1, if it were, it would be a right angle. BAC would be a right angle. We're going to skip C for just a moment, so just bear with me. I'm going to leave about this much room for C, and we'll see if we can fit it in that space a little later. Right now, we're going to move on to letter D. Let's see. Circle C has a 5-inch radius. X, Z, and YZ are tangents to C, and Z is a point exterior to C. There's no way I'm going to be able to do this without drawing it out and seeing exactly what's going on. If XCY is a right angle, keep in mind Z is my exterior point. X is a point on the outside of the circle. Y is a point on the outside of the circle. And C is the center of the circle. And I know that XCY is a right angle. That's the interior angle between my radii. What is the area of quadrilateral CZXY? Now, hey, look at that. It's already drawn out. Point C is the center of the circle. X is on the outside. We don't need this line anymore up here. I accidentally left that there from a previous one. All right, and X and Y are on the outside of the circle. They're going to be points of tangency for lines passing through them. Okay, and then we have point Z that's somewhere on the outside of the circle. Now, here's the thing that I know. I know that XCY has to be a right angle. But now, if there's a point on the outside of the circle through which I can pass tangent lines through X and Y, and it's actually locked into one specific point. Because what has to be true? Well, first of all, this has to be a right angle with the radius CX, okay? And there's only one line that accomplishes that. It's going to be something like this line here, okay? And then this one has to form a right angle with CY. Ooh, this is going to be rough. Let's see. I can move this manually. And then I need to make this like that. Okay. And it's going to be a point of tangency. I'll clean that up in just a second. But there's only one line I can draw that forms a right angle with CY. So it's going to look something like that. This has to be a right angle as well. And then what is my shape? This is a square. This is a square shape. So going back to here, if circle C has a 5-inch radius, what is the area of the quadrilateral? If one of these sides is 5, to find the area, I just do 5 times 5. It's going to be 25 inches squared. 25 square inches. All right. And then lastly, letter E. A decorative Illuminati window is shaped like a triangle with an inscribed circle. If the triangle is an equilateral triangle, the circle has a radius of 3 feet. Uh, and CQ is 6 feet. What is the perimeter of the triangle in simplified radical form? Okay, so again here, we have to think this through to figure out what's going on. And I'm guessing this is going to have to do with right triangles. And sure enough, look at this. I have a little tiny right triangle here. How do I know it's a right triangle? Because the radius has to be perpendicular to the tangent line. Inscribed circles are inscribed because the sides of the triangle make tangents with the circle. So I'm going to figure out whatever this side is, and then we're just going to have to multiply it times 1, 2. Is an equilateral triangle, so it's going to be 3, 4, 5, 6. It says it's equilateral right here. Okay, so let's figure out what this unknown side is. This is going to be a Pythagorean theorem problem. It's going to be 3 squared plus b squared, because I don't know one of the legs, but I do know the hypotenuse, equals 6 squared. So the rest of this problem looks like this. I've squared 3, squared 6, subtract 9 from both sides. B squared equals 27. If I take the square root of both sides, b is the square root of 27. Square root of 27 breaks down to the square root of 9 times the square root of 3, which is 3 times the square root of 3. You need to multiply that times 6. 1, 2, 3, 4, 5, 6 to get 18 times the square root of 3. And that is the perimeter of my triangle.